Welcome to a lesson with Dr. Powell. Let's take a look at how we can come up with the equation of a plane in 3 dimensions. Okay, so just like for a line where you need a vector and a point, and that determines a line, actually, that's all you need for a plane too. That determines a plane. How so? Well, think of a plane and think of a vector that's orthogonal or perpendicular to that plane, kind of, but perpendicular in every direction here, just heading up from that plane. This direction, either going this way or that way, back and forth, is the only way that you can have anything that's orthogonal to the whole plane. It's just right on that line. So really, any vector that's orthogonal is going to determine a plane if we have a base point, a starting point right here. So that's all we need, a point and a vector. Okay, so let's try this out. How does that actually work? Okay, so let's think, and maybe I'll draw another picture here of the same type of thing. Let's have V coming up here, and let's have P naught being here. And pretty much we want to find a condition for how Q can be in this plane. In Q, let's just make it arbitrary, be an arbitrary point in space. So suppose it's X, Y, Z. And let's give a particular example. Let's let this vector, this point right here, and we'll describe it as a vector as being, let's just do 1, 2, 3. That's a nice one. Okay. And then we have a vector that's orthogonal to the plane. And let's let that one be, let's just pick one like 1, negative 3, and 5. Okay, so that one's perpendicular or orthogonal to the plane. Now, we need a condition for how things are orthogonal to each other. So the condition that makes things, or that checks to see if we have orthogonality, is dot product. If the dot product between two things is 0. Because remember, a dot product is the same thing as projection onto something as long as that something is a unit vector. But if that projection is 0, you rescale that all you want, it'd still be 0. So even if it's not a unit vector per se and it's 0, it's still going to be orthogonal with 0 projection. So orthogonality is all we need. All right. So what we need is anything. So, well, what if we drew a line from here to here? This is in the plane, right? Because we assume that Q's in the plane. So assuming that vector's in the plane. So we really need that these two vectors are orthogonal to each other. Okay, so if this one is orthogonal to that one, we need their dot products. The dot product to be equal to 0. That actually determines the equation of the plane, a dot product being 0. We need a vector, which is V, or orthogonal one, dot another one is equal to 0. So this one right here is going to be this vector. We need to figure out what that one is. Well, let's think. From the origin, this is a vector. That's a vector. And we know that this one plus this one is that one using arrow math. Well, that means that this one minus this one is that one. So we simply take Q minus P naught, and that's what this is going to be. So this is V, and this one is Q minus P naught, which we can do component-wise. X minus 1, Y minus 2, Z minus 3. So we have X minus 1 and Y minus 2 and Z minus 3. And that dot product needs to be 0. So we multiply component-wise, and then we add the results. So we get 1 times X minus 1 minus 3 times Y minus 2 and plus 5 times z minus 3 equaling 0. This is the equation of the plane. Now we can multiply this out. 1x minus 1 minus 3y plus 6 plus 5z minus 15 is equal to 0. And let's see, negative 1 and 6 would be 5. And then 5 and negative 15 would be minus 10. Put the 10 on the other side if you want. Okay, so we could have 10 is, we have x minus 3y plus 5z. This is the equation of a plane. Notice these coefficients, 1, negative 3, 5. They're precisely orthogonal vector. And we didn't have to use this one. We could have used any multiple of this one, or rescaling, multiply this vector by any constant, and it would still be orthogonal. It would still give us the same equation over here. So it's kind of neat, though, that if you have an equation of a plane, you can read off what an orthogonal vector is to it just by looking at the coefficients of x, y, and z. Thanks for watching.